All right. So applications of this circular motion. Things move in circles all around you all the time. Around you, just kidding. So we derive the centripetal acceleration as being v squared divided by r. And then we did a little lab to try to explore that a little bit more. Okay, so first scenario, let's say we have a car, and it's going to do like a U-turn in a flat parking lot. So I'm trying to draw the path of a flat circle there, but I'm not an artist, so it struggles there. Okay, so there's like the dotty dot dot line, and here are the tires for the car, and here's the bumper of the car, and here's the back windshield of the car. Do you kind of get the idea? The car's kind of going around this curve. What keeps the car moving in the curve? Why does the car not slide out of the curve? Hint, hint. There is a normal force on it, but there's also a friction force, and if it's on the earth, there's a gravitational force. So the center of this curve would be over here, and you would have a gravitational force due to the earth, and you would have a normal force due to the surface. But then to keep it moving in the circle, the friction force has to be directed towards the center of the circle, which makes this friction force point towards the center, which makes the friction force center seeking or centripetal. So the forces you already know can be centripetal if they're pointing towards the center. There is no such thing as a centripetal force. There are forces that are pointing towards the center, and those are centripetal. There is no singular force that is the centripetal force. So if I were to sum the forces acting on this thing on the x direction, I look at it in the x-axis, those forces are not balanced, so it must be equal to MA in C because I know it's moving in a circle. The center of the circle is over here. When I look at the forces I've drawn in the y direction, they look balanced. So, and I know the car doesn't float up into the air and it doesn't sink into the ground, so they must be balanced. So then the force of friction pointing towards the center would be equal to MAC, and the normal force minus the gravitational force would be equal to 0. Now, if I remember correctly, the friction force is what? The coefficient of friction times the normal force. And the normal force would be equal to the weight in this case. And we can find the weight by multiplying the mass times the gravitational field constant. So I can make a substitution where mu mg is equal to MAC. Does the mass of the car matter? It cancels out. So we'd have mu g is equal to AC, but AC is v squared over r. So what's the maximum speed we can have going around this curve? Well, you can solve for the velocity, and it would be r mu g all under the square root. Looks like a root rug. So the next scenario I want to look at is more like what you saw with the stopper that you were swinging around your head, and that was that the string was attached to the stopper. This is the same sort of situation where you could have had, so here's the pipe like this, and the string went through it, and you had another mass hanging over here. Okay, so the stopper was going around and around in this like conical pendulum type path. But this could be you sitting in one of those swings at the amusement park and the disc goes round and round and you sit on the swing and it goes faster and faster. And what do? Kind of swing out. There's one at Six Flags like that. Also, have you ever been in an airplane and the airplane takes off and then you can tell that the airplane is changing direction? You start feeling that banking. The airplane turns. You feel the bank. Or you're coming into the airport and it has to circle. You feel that banked. So this is the same thing. Like if the plane is flying around and it's banked, it's banking. And we call it banking because it's like at an angle, it's not flat. Okay. Also, have you ever been around a real curve in a real road or accidentally watched NASCAR? So the track has these curves. Are they flat? They're super angled.